Hey, welcome to the second day of the summer school on understanding large language model understanding. Yesterday was exciting, and it'll soon be online for those of you who want it on YouTube. Today, we start with Eva PORTELANCE, who has just made a transition from McGill and Mila to, you're still at Mila?
Yes.
Okay, so still at Mila, and then to the École d'Études yes, HEC here in Montreal. Her research intersects AI and cognitive science. She's interested in studying how both humans and machines learn to understand language and reason about complex problems. Welcome.
Thank you. Thank you. Thanks for those who came in person. Hello to those online. Thanks for coming to this talk on what neural networks can teach us about how we learn language. So I thought I would start us off today by highlighting the problem that I'm going to be talking about today, which is learning language. So why is this an interesting problem to study, and why is learning language so difficult? Well, imagine that you are learning your first language for the first time, and you're on a walk with another native speaker, possibly your parent, and suddenly you see this creature run by. And your parent says, "Get a guide." This will be a familiar problem to some of you, I'm sure. So your job as a language learner is to figure out what this could possibly mean, right? Maybe it means rabbit. Maybe it means white rabbit. Maybe it means look there or careful. The point being that it could mean a whole slew of things, right? So how is it that language learners figure out a way to map new meanings to words? This is the problem, at least one of the big problems that we're interested in when studying language learning and language acquisition. Now, we may no longer be the only kid on the block that seems to be able to learn to map word meanings. So we now have these models. Some of you have probably heard of large language models or just language models in general that seem to be able to map new words to novel meanings. And so what I try to do in my research is to figure out ways that we can sort of bridge these two fields, right? On the one hand, cognitive science, on the other, AI, to study questions about language learning, learning more generally, and reasoning, both in humans and in our models. Now, this bridge is it's a two-way street, right? On the one hand, we could think about how we can use our models to influence the types of design decisions, use what we know about how humans learn language to influence our design decisions and how we create new models. But on the other, we can also think about how we might use these models to help us answer questions that we might have about how we learn or how we reason. And so that's really the direction we're going to concentrate on today. So focusing on what models can teach us about how we learn. Now, the idea of using models to study human language learning and processing is not a novel idea, right? It's been around for quite some time, starting back in the 80s with a movement called connectionism. Though traditionally, connectionist models were seen as cognitive models. So what do I mean by a cognitive model? So a neural network is a cognitive model when it establishes clear connections and assumptions about the relationship between human cognition and the actual model design, okay? So the one we might observe a result in our model, we could then, through our linking hypotheses, conclude that they might also apply to the human mind. So cognitive models create these linking hypotheses, right? And they do adhere to a philosophy from philosophy of science, which is cognitive realism. So they commit to being cognitively real. This means that their goal is, or realism is seen as a goal in for science of discovering the truth, albeit approximately. So our models are expected to reflect the unobserved reality of human learners. Now, I'm sure most of you in the room today and online likely believe that large language models do not reflect cognitive realism, right? So that brings us to the question that I want to ask today, which is, can modern neural networks still be useful for studying language learning without fully committing to cognitive realism? Is there a way that we can still salvage this relationship between using these models to help us answer questions without making all of those clear commitments when we design our models? I'm going to argue that yes, okay? I'm going to say that there's sort of two ways we can think about these using these models, and sort of three approaches that fit under those. So on the one hand, we can use models as tools. On the other, we can think of models as sort of independent minds that we can study. As models as tools, I'll talk about an approach that I call weakly cognitive modeling. And then as studying models as minds, we'll talk about two approaches, one called proof of concepts, and the other that I termed hypothesis generation models. So you'll see in the top corner of my slides, a little tree that appears. That's going to be sort of the map of today, so you can follow along where we are mapping these different relations. So we're going to be doing pre-order depth first search today. So we're going to be moving down the tree, first talking about models as tools, then talk about weakly cognitive models. We'll give a concrete example of how we might apply that approach in language learning. Then we'll talk about models as minds, proofs of concept, concrete approach, and then hypothesis generation, concrete example. Okay. So models as tools, what do I mean? So an obvious way that we can use these models is simply as processing tools, process data, to cleaner data, generate new data. But that's not what I mean when I talk about models as tools. I really want to talk about studying the models themselves, not using the models as something part of a pipeline for our research. So how does that work? So we are all now familiar with these large language models, or just language models in general. And it turns out that these types of models can be really interesting to study and help us understand people, because they are trained on data that we, at least until now, have produced and generated, right? And so one of the ways that's been super fruitful in the field of cognitive science and connected fields of using these models is to study their word embeddings, or these vector representations of the meanings that they learn for words, okay? So using these spaces, we've been able to figure out that we can use all sorts of operations on these representations of meaning, measuring things like similarity between words, or even other types of relations. So really what's happening here when we use models this way is that models are giving us a way to have a quantitative representation for an unobservable concept, right? So using this approach, we were able to measure all sorts of different things that we weren't necessarily able to clearly represent before. So this has given us a way to measure things like social bias, right? Things like word associations or meaning maps, and how we might associate concepts in the mind. And finally, things like cultural shifts, right? So measuring on a larger scale across people how different meanings may change. So in this models as tools approach, what we're really doing is we are saying that some of the internal representations of our models can be extracted, right? Here, word embeddings, and used as an approximation for another unobservable concept in people. So we're no longer making assumptions that the whole model, all of its internal representations and processes are cognitively real, but we may make the assumption that some of those may be. So this is an approach that I call weakly cognitive modeling, right? Because we can use at least some of that, some of those connections, but maybe not all. So I'll give an example now from my own research where we're going to use this weakly cognitive approach. We're going to build a linking hypothesis between models and people about word predictability. So we're going to use a model to measure the predictability of words in context, and use that as a proxy for what might be the predictability of those words for a person, if presented with the same input. Okay. So using this linking hypothesis, we're going to try to answer a question about in language learning, which we have, which is, are more predictable words in children's linguistic input learned earlier by kids? So are kids actually sort of tracking those core occurrence statistics on a word level to help them learn them? Now, based on the linking hypothesis we had, we can sort of reword this question more specifically as, are more predictable words for a language model trained on child linguistic input learned earlier by kids? Okay. All right. So to situate this project, I first want to give you a couple observations about what we do currently know about how kids learn. So it turns out that at least in the first couple of years, kids are pretty consistent in the order in which they learn words. So a kid will say a word like milk before they say a word like sad. And this is because, at least in part, these ordering effects seem to be predicted by how frequently these kids hear these words. So milk is just much more frequent, at least early on in children's input, than a word like sad. And also in terms of how concrete their meanings are. So milk is, a bottle of milk is something you can point to. In the world, it is very concrete, whereas a concept like an emotion like sad is much more abstract. And so we know that these are two things that do predict these ordering effects. So kids are relatively consistent, and at least on a frequency level, statistical learners in the case of words. We also know though that there have been results showing that kids do track things like co-occurrence statistics, at least when they're trying to learn new word boundaries. So in this particular project, we were interested in seeing whether or not those tracking of co-occurrence statistics could also be happening at the word meaning learning level. Now, when we talk about predictability in people, we don't use probabilities. We instead use a concept called surprisal, which is the negative log likelihood of some outcome given a context of some kind, right? And this is used because it's a pretty good measure of human processing difficulty. So when we're going to think about predictability, we have to kind of switch it on its head, because surprisal is negative is sort of the opposite of probability, right? So something that has low surprisal is very predictable versus something that has high surprisal is much less predictable. Or if you want to think about it in terms of like the word surprising, that can help to kind of get that notion, though it's not necessarily a measure of surprise. Okay. Now, the final concept I want to introduce, in case some of you are not from linguistics, is the idea of lexical categories. So there are different types of words, and they have different sort of grammatical functions, and we call these different lexical categories. So things like nouns are words like milk, papa, house, dog, right? You probably all know what nouns are. When we talk about predicates, we mean verbs and adjectives. So words that can either cause a state change or describe an action of some kind, okay? And then finally, function words. Function words are all these little grammatical words that we have in a language, such as inside, more, and you, me, all these types of little words that have actually really important functions in words, in language, but their meanings are are much more abstract, okay? These are also called closed class words because we don't introduce new ones very often to language, so they're closed classes. All right. So based on the research question we were starting with, we had our more predictable words in a language model trained on children's linguistic input learned earlier by kids. So we have two variables here that we're interested in, right? Predictability, which we're going to measure as surprisal. And then we have the age at which kids are learning words. So this is going to be something called age of acquisition. So age of acquisition is an estimate of the average age at which kids start saying a word, okay? So let's look, just to give us a sense of what the relationship might be between these words, let's plot them, right? So on the x-axis, we'll have language model surprisal, and then on the y-axis, we'll have the age of acquisition in months. Okay, so since we're in Quebec, let's do some Quebec French. So I've plotted some nouns here from Quebec French to give us a sense. At the bottom there, you see lait, which means milk. So that's that example I gave you earlier. So learn super early, right? Around 16, 17 months on average. Kids start saying that word, has sort of average, somewhere in the middle of surprisal. And then we have words a little higher, like doigt, meaning finger, learned a little later, and then robe, learned even later, and so on. So you get some examples of what nouns look like. What about verbs? Here we get a slightly different picture, right? So at the bottom here, we have tomber, which means to fall. Kids say that very early. And then as we move up, we have things like nager, to swim, écrire, to write. And then really high up, so much later, we have much more abstract verbs like choose or think, choisir, penser. And then finally, some function words. So at the bottom, if you have kids, you know this comes real early too. Encore, more. I like saying that very early and a lot. And then we have, as we move up a little more, we start to have like moi, me. And then later we have you, and all, tout, all. And then later on again, we have more abstract concepts like même or same, and par, by, and so on. Okay. So that gives you just a sense of what exactly we're trying to do here, right? We're trying to predict this age of acquisition based on this surprisal measure. So if we wanted to fit some linear models and look at the sort of the coefficients we're going to expect here. So what should we expect? Well, given our hypothesis, we actually think that words that are less predictable should be learned later, right? So words with high surprisal should have higher ages of acquisition, while words that are very predictable in context should be learned earlier. So these will have lower surprisal and lower ages of acquisition. So we're looking for a positive coefficient, right? A positive relationship. So let's look at some results. So I'm gonna, on the x-axis, this is just the coefficients. So really we want to see whether or not they're positive or different from 0. And then on the y-axis, we have our LSTM surprisal. And LSTM is a type of language model that we've done this with a bunch of different language models. And then we also have unigram surprisal. So this is it's basically frequency, just log transformed, and we change the sign on it. So we have frequency there mostly as a way to make sure that we're in the right direction, because we know that frequency does predict age of acquisition. And then we want to see really what's going on with LSTM surprisal. So here we're controlling for frequency. So you can think of this as like the predictability beyond frequency. So when we start considering context beyond a single word, what happens? Let's consider what happens for nouns. So for nouns, as we'd expect for frequency, more frequent nouns learned earlier. Okay, we have that positive coefficient. But when it comes to our language model surprisal, we're right on the 0 line here, meaning that for nouns, considering more context doesn't really seem to matter. What about function words and predicates? Here we get a really different picture. So here we do actually see that considering context beyond frequency, so considering previous words that were said in a sentence, actually does start to matter for function words and predicates. And as it turns out, this pattern holds for a bunch of different languages. Here's American English, here's German. And so we see similar patterns cross-linguistically, a bunch across different dialects and different languages. So in terms of the question that we had, are more predictable words in children's linguistic input learned earlier by kids using this language model predictability as our measure for word predictability in people? We were able to find the answer that yes, for verbs, adjectives, and function words, but no for nouns. Why might this be? So the nouns that children learn very early on tend to be very concrete, right? They tend to be things that you can point at in the world, like, or that you can see, right? So as the kid hears the word milk, they likely have a bottle in front of their face or their mother, versus, and if they hear a word like tree, they may have a parent pointing at the tree or something as they're on a walk, right? And so they may be getting a lot of other forms of input that are helping them learn these words that are more informative than using the linguistic context only. Whereas verbs, adjectives, and function words get a lot of their meaning from the context in which they appear, right? And so there it actually makes sense for kids to actually consider the context in which these words are appearing to try to learn what they might mean. So what did we learn using this weekly cognitive model approach about how we learn words and how we learn language? Well, it seems to be the case that humans do pay attention to word co-occurrences when they're learning their meanings, but they don't do it the same way for all words. So learning has to require diverse learning strategies and possibly also diverse inputs, okay? All right. So this was a sort of, this weekly cognitive models is what I sort of consider using models as tools, right? And so models as tools introduces this new dimension to what the goal might be for modeling. which is instrumentality, so instrumentalism. So instrumentalism is, again, from philosophy of science, a philosophy that says that the goal of science is accurate description and prediction of observations. So our models are seen as tools for understanding and predicting observable phenomena in human learners. In its purest version, you would make no commitments whatsoever to the reality of the unobservable. So my colleague Masood Jaspi and I have argued that we can kind of think of, if you don't consider the purest version of instrumentality, you can kind of think of these two goals as directions in which that might delineate a space in which we might think about how we design our models. So on the one hand, if you were designing a cognitive model, we may be trying to maximize for cognitive reality in some way. And so this would be, these early cognitive models and dating all the way to, the mid-2010s. But on the other hand, we may also want to start thinking about instrumentality as a valid direction, which we might consider pushing our model. So the project I just showed you, a weakly cognitive model, may not make as many commitments to cognitive reality, but also gives us some commitments to instrumentality. Now, what if, like large language models, we can't really make any commitments to cognitive reality? What do we do then? What if we find ourselves in this space where really we're designing models purely for instrumental reasons? Can they still inform our understanding of language learning in people? So this is where this sort of other set of approaches comes in, where we start to think about these models as independent minds that we can study, or if you will, as sort of a separate species of learners. So here, we can't really make any commitments to cognitive reality, at least initially, right? Instead, what we might do, what we are presented with is that as we're sort of moving towards these goals of instrumentality, we've been developing models that have learning environments that are becoming more and more realistic. So though the models themselves inside may no longer be realistic, the learning environments in which they are learning are becoming more realistic. So that's in terms of, the type of data they're presented with. They're presented with real language, large amounts of it, and rather than, say, constructed data sets. Some of them are even presented with grounded input, right, with exposure to images or video or even sound. And finally, some are even presented to social interaction in some way, either with other models or even humans in the loop in some way, right? And so these new models that we've developed have sparked really an interest in studying how they might have sort of emergent behaviors that arise from these realistic inputs, right? And so there's a whole slew of research that's been studying how these models might develop, forms of quote unquote understanding of language or grammatical knowledge that they might encode, and whether or not the behaviors they do end up seeming to produce seem to match those that we see in people's judgments. Now, though most of this research, sometimes referred to as like Bertology, wasn't necessarily about understanding something about people's processing and people's learning, it did present us with this new opportunity, which is to use these models as what are called proofs of concept. So how do proofs of concept work? So say you observe some behavior in human learners, and we have sort of two opposing hypotheses about where this behavior originated. Either that it is in some way innate, so that at least some part of the knowledge required to learn it has to be there from the start, or that you have some kind of learning bias, or in its strongest form, it's just there, you're born with it. Or we might have a second version of this hypothesis, which is that the behavior is fully learned in some way, right? So it can be learned from really general statistical mechanisms. You don't really have to have any prior biases, and that actually, we learn this purely from experience. There's a lot of those debates in language acquisition. Okay, so we have these two hypotheses. Now, if we have a model that we can argue has a learning environment that is either the same or somehow inferior to the one that humans have, and that the model can still learn this behavior, then we have proof of concept evidence in favor for the learned hypothesis. what does it mean to be a proof of concept evidence? So importantly, it doesn't mean that we have evidence that humans are learning it, right? All we've done is we've shown that the model is able to learn it, but it does show us how in practice it is possible to learn this behavior, right? So it gives us evidence that this is a plausible hypothesis. All right. So I'll give you another example of how we might apply this in practice to answer a question we might have about language learning in kids. So again, can hard words like and, or, behind, in front, and more, fewer be learned from general purpose statistical learning, or do we have to have at least some forms of innate knowledge or biases towards learning the reasoning skills we need to understand these words? Given time constraints today, I'll concentrate on the pair and and or only, but if you're interested in the others, I'm happy to talk about them after the talk. Okay. So to answer this question, I'm going to be using grounded language models. These are language models that learn both from images and from text. So we're going to use VQA models. VQA stands for visual question answering models. These are models that are trained to answer questions about images. So this is an example. We have this like block world image and the question, what color is the map object to the right of the large block? Okay, so this is a type of data they're trained on, and they're trained to answer these questions, right? So that's their particular objective during learning, but as a sort of a strategy that ends up developing, they end up defining ways to map the meanings of these words to these images. So they're mapping some form of, what's the concept of color in the image, what's an object, what's right of, to the grounding they have in the images. So in this particular project, we use this data set called the Clever data set. So this is an example of a training pair from that data set, which is these images from a block world and all sorts of questions that were designed to study whether or not these models could develop complex reasoning skills like logical reasoning, spatial reasoning, relational reasoning. So here we have an example of spatial reasoning to the right of. Okay. And then the model we'll use was, at least at the time, a state-of-the-art model. It does very well on this task, which is the MAC model. And we'll look at whether or not, how this model is learning the meaning of and or. Okay. So one of the reasons we chose this particular data set is that it has a fully defined generative model for its language, meaning that we actually have the definitions that were used for these words to generate the answers to the questions. And so in the case of and or, we have the logical operators, basically, and or. So and means expects a no answer, for all contexts unless both propositions are true. So otherwise it's always going to be no. And then or is what we call an inclusive or. So it's an or that is true as long as at least one of the propositions is true, including the case where both are true, okay? Now in natural language, there exists another or, which is exclusive or. So exclusive or is a little different from inclusive or in that it is actually false in the case where both propositions are true. So you can think of this as like the either or, right? It's super common in natural language because we often have two propositions that are conflicting in some way, right? So like if I offer you juice or milk, usually you don't want both at the same time, right? And so people will tend to interpret or this way. Okay, so what do kids do? So kids learn and before, we know this, okay? What about inclusive or versus exclusive or? This is where the picture is a little more complicated. So exclusive or is more common in their input, okay? They hear a lot more cases of exclusive or, and so a fully, learned hypothesis would expect exclusive or to therefore be learned first, okay? If all you were doing is sort of considering their experience and that their experience should be what predicts the order in which they learn these words. Now, unfortunately, children seem to understand inclusive or before exclusive or. So some have proposed that what might be going on here is that actually kids learn inclusive or first, and then they develop exclusive or through pragmatic reasoning. So by thinking about the alternative possibility that, maybe you would have used and in that context if you actually meant to consider whether or not the two propositions were true. Now, given that we have sort of this contradiction where exclusive or is more frequent in the input, but inclusive or seems to be understood earlier, some have argued that this is an argument in favor for an innate hypothesis, that we somehow have an innate understanding of inclusive or just basic logical connectives. Okay. So what I'm hoping to do today is to use a proof of concept with language models, visually grounded language models, to show you that we can still salvage a learning hypothesis, even in this context where we seemingly have this contradiction. Okay. So how do we figure out whether or not our models have learned and or, and what they're encoding for these words? So we're going to use a probing technique. So we're going to be developing a task where we have models answer questions that aren't part of their training. Where we control for every possible possibility of that language, every possible combination of words in certain templates to see whether or not they're understanding words. So I'll give you an example. So here's an example of a probe question. So are the small things that are cubes and green? So then you would have to answer yes here. Right? We have two green cubes. And this would be an or one. Are there red spheres that are small or rubber? Well, first we have objects that are both. So here, if you had an inclusive interpretation first, you would answer yes. But if you had an exclusive interpretation, you would answer no. So what we do is we go through, we have these templates like this, like are there referent that are X and or Y? And we try every possible combination of referent X and Y values within our generative model to make sure that we can control for, those being an issue somehow in how the model interprets these questions, where the meaning really across that has to do with the specific word and more. Okay. So how do models do on these probes? So we can look at how they do over time during learning. Here's what they learn. So they actually learn pretty quickly to interpret and or, right? I should say that or here is only in the non-ambiguous cases. We'll look at the ambiguous cases after. And so they do quite well. This is sort of an out of distribution task in the sense that these are questions it's never seen before. On pictures it's never seen before as well. So performance is not 100%, but it still does very well. Okay, so what happens in the cases where we have these ambiguous or interpretations? Well, here, interestingly, we actually see this rise in exclusive interpretations over time. So though models are technically being exposed to questions that were created using a generative model that had an inclusive or, over time, as they're exposed to more and more language and learn their languages, they actually develop this sort of exclusive interpretation. So why might that be? Well, one possibility is that somehow models are learning to be sensitive to the alternative that exists, and, right? So once they sort of acquire and, they may start changing their interpretation for what or should mean. So what happens if we remove and? Do we still see that rise, or do we sort of see a plateau in its interpretations of exclusive or? So here's what we had before with the alternative. If we remove the alternative, we no longer see that like rise all the way to that 50%, but it's closer to the performance we'd expect, given that it performs around 75% of the time correctly on these probe questions. Okay, so using this proof of concept approach, what have we shown? Well, function words requiring skills like logical reasoning can be learned from grounded language using general statistical mechanisms. On top of that, we've also shown that it's possible to learn to be sensitive to alternative expressions, which is a precursor to that pragmatic reasoning we need, and that these can follow from general mechanisms. So you still can have a case where you may have one interpretation more common than the other in your input, yet learn a bias over time that leads you to have a pattern that may no longer map specifically to the frequency of these words in your input. So in this case, we did not make any really commitments to cognitive realism in our model, right? It was really more about instrumentality. and showing what was in theory possible, in practice possible with models, and theory possible with people. So this is more of a proof of concept approach. All right. Now, proof of concepts definitely have their limitations, though they're still really interesting. But what is it? What do we do if we want to find a way to have these commitments to cognitive reality, but possibly post hoc, right? So if we're starting from these models that already exist, or models that weren't necessarily designed to be cognitively real, is there a way that we can still move back to this desirable space where we can also consider not just instrumentality, but cognitive reality again? This is where this next and final approach that I'll talk about is going to come into play. So again, we're thinking of models as independent minds that we can study. So we're studying neural networks as independent learners, just like proofs of concept. But we're no longer trying to distinguish between existing proposals. Instead, we want to study these models in their own right and see whether or not new hypotheses about how language may be learned can emerge from these models, and if there's a way that we can then transfer those hypotheses to people. So this becomes especially interesting when we start to consider causal hypotheses, right? So unlike with people, where you, for moral reasons, can not really design ablation studies, you can do this with models, right? So if you have a hypothesis about whether or not some prior X, be that some distributional information in your input, or a learning bias that's encoded in your model or something, causes some learning outcome Y, we can figure out whether or not there may be a causal relation, direct or indirect, between X and Y by either modulating or removing X and seeing whether or not that modulates or removes Y, okay? And so this will give us evidence for a causal hypothesis. Now, this is where this hypothesis generation model comes in. Say we have a model where we've shown that we have this causal relation, and we have this hypothesis. How do we then go to make that hypothesis about people? Well, if we can show that X and Y are also present in the learning environment of children and kids, we know that causal hypotheses make testable predictions. So though we may not be able to look inside the mind and figure out whether or not that same relationship happens, or design the same experiment, ablation experiment with people, we do have these testable predictions that we can actually go look for in people. And if we find evidence for those testable predictions, then we can actually say that we can extend this hypothesis to being possibly cognitively real in people. So this then we have that this hypothesis may also be true for people. Okay, so an example of using models for hypothesis generation, again, to study a question about language acquisition. So here we're going to look at something called the shape bias. So why do we have a shape bias? How did it emerge in both language and perception in the first place? I'm going to argue that the shape bias, I'll show you what a shape bias is the result of something called communicative need. And that we design efficient communication systems, and this is what leads to the shape bias. Okay, so what is a shape bias? So if I show you this object and say, that's a DAX. Now I show you two more and say, no, there's another one. There's another DAX. Most of you will assume that I'm referring to this object here, okay? So this is called the shape bias. So it's a tendency to assume that new lexical categories share shape features rather than other possible perceptual features like color or texture and so on. It's a bias that seems to be learned. It appears around the age of 2, and we have it until adulthood if you just experience that little experiment. Most of the previous literature has been about how it might be learned, so what types of methods lead to its acquisition, and whether or not it's real. But all of this research is sort of predicated on the shape bias existing in the parent's language. And so the question we want to ask today is, why have it there in the first place? Because we have this sort of chicken and egg problem. If it's learned, but it has to be in the parent's language in order to acquire it, why is it there? Okay. Well, it turns out that humans are very efficient language designers. So we tend to develop solutions to communication problems that fall along this sort of Pareto frontier between information loss and complexity. So what do I mean by that? So we design languages that allow us to communicate successfully without losing information or being misunderstood. But we also take into account that we have limited memory resources, and so we try to design languages that are as simple as possible without losing that information. An example of this, say, from semantic systems, so around kinship systems. Here's an example where we have English and Northern Paiute. So in English, we don't make the distinction between your paternal or maternal grandmother, right? They're both grandma or nana or mammy or whatever, right? So whereas in Northern Paiute, they do make that distinction. And so Northern Paiute has a slightly more complex kinship naming system. But if we sort of plot where Northern Paiute is yellow and English is red, both sort of fall along this Pareto frontier where they don't lose any information in terms of the communication they have. So why is this? This is because both information loss and complexity are modulated by something called communicative need. So it's the need of a particular population to communicate certain distinctions. Whether your grandmother is your paternal or maternal grandmother may not have that much cultural significance in an English-speaking population, but in a population that speaks Northern Paiute, it might actually have cultural significance. And so it's important to be able to communicate that distinction easily, right? And so that's what we talk about when we talk about communicative need. It's the need of a particular population to talk about certain distinctions. And if there is that need, then you expect those distinctions to be there. Okay, so I'm going to argue that it's these same sort of efficient communication strategies that lead to the shape bias, where we have a need to communicate shape distinctions. And in order to sort of model how that happens and why there is that causal relationship, I'm going to use neural agents. So these are each independent little neural networks that are both language models that can see images as well, that can communicate with each other through discrete channels. So they can talk to each other, they can send messages. So we have, they play games where they take turns being listeners and speakers, and they're trying to come up with a language somehow. So if one is a speaker, it'll have an image of a target object that it needs to communicate to the listener, while the listener will have another image of that target object as well as some distractors. And based on the message that the speaker will say, they'll have to make a choice about what they think that target object might be, okay? So if the choice is correct, the speaker gets a reward in some way, and if and the listener also gets to learn from making that mapping correctly of that word to that image. So as they do this, they slowly develop a shared naming system for these objects. Now, since we want to talk about communicative need, I have to have a way to quantify what it means to have higher need to make shape distinctions. And the way that we do that is by introducing shape games during learning. So shape games are games where the target object, in some way, it has, in order to correctly pick it, you have to have a name for that object that somehow communicates shape distinction. Because here, for example, we have this other distractor that is the same in all aspects, visual, perceptual aspects, to the sphere, except that it has a different shape. So whatever word we use to talk about this purple, large, metallic sphere, it has to somehow encode a distinction based on shape in order to be successful at this particular game. So we can quantify communicative need in terms of the proportion of shape games that are seen during learning. So if you have a lot of shape games that are seen while you're coming up with your language, you have a higher need to make these distinctions based on shape. Okay. So in the games that will have these agents play, they have 320 unique objects that they have to somehow communicate about. And these objects can differ in terms of their shape, their color, their size, and their material. Here's some examples of what those objects might look like. And then this grid here is 320 different little squares. So the task that these models are trying to do is they're trying to figure out an optimal way to partition this space into lexical categories, okay? So we do the same thing when we come up with a language, right? If I say, this is a screen, it's not, I'm not referring to this particular screen necessarily, but you know that the meaning of screen is a shared set of like perceptual properties that represents that lexical category. And so the same is happening here, where these agents have to figure out what is a word that represents that shared set of perceptual categories. Okay. So since we want to argue that the shape bias follows from these efficient communication strategies, we have to first show that these agents indeed have these efficient communication strategies. So let's look at what happens to information loss as a function of communicative need. So on the x-axis, we have communicative need. So this is the proportion of shape games. So at 0, we're just randomly sampling games, right? We're just randomly sampling images. Whereas at the opposite end, where we have 40%, 40% of those games are conditionally sampled so that they have at least one distractor that is the same in all aspects except shape to the target. And then on the y-axis, we just have accuracy, right? So if they're inaccurate at a game, they're losing information, right? So that means they were not able to correctly communicate. So we can measure how much information is being lost between the agents. Okay. What happens here? So I'm plotting here the performance on test shape games of the models as a function of how much shape games they saw during training. And as we see, probably not surprisingly, as we introduce more and more shape games, models start to develop languages that allow them to make more and more shape distinctions. They do better and better at shape games. The dotted line there is just the overall accuracy on any game of the models. You'll see a slight drop at the end there. That's because shape is very difficult. So the models use what are called convolutional neural networks to process images. And these tend to have an innate bias towards local features. So shape being much less, being a much more sort of large picture feature, it's a little harder for them to process these. So as we force them to play more shape games, it just becomes generally a little bit difficult for them. Okay. What happens to complexity? So same thing. As we increase the need to communicate about shape, we also end up developing languages that are more complex in terms of the shape distinctions they can make. Complexity here is measured using the mutual information that exists between the embedding space, so the language that these models develop, and the target labels for these objects. So whether or not those embeddings can be used to determine different shapes, different colors, different sizes, different textures. Now, this is actually a pretty surprising result, even though I've kind of introduced it as like, this is obvious. These agents actually do develop optimally efficient languages. So these gray dots are theoretically possible languages they could have come up with, just some sampled. And the colored dots are the ones that our agents actually did come up with. So we can see that they fall really along this Pareto frontier, just like human languages seem to. And both information loss and complexity are really modulated by communicative needs. So great. Agents develop efficient communication systems. What about the shape bias? Why does the shape bias actually follow from these strategies? And why does it follow from that high communicative need for shape? Well, let's consider what happens to other perceptual features as we increase that need to make shape distinction. So here I'm plotting color. So initially, when we're randomly sampling, you'll see that color performance on color games is really high. This is that fact that I was telling you that so CNNs really like localized features. Color is very local. It's the pixel values, right? So it's very easy for them to learn a system based on color. So they actually have a sort of innate bias towards color. But then what happens as we increase this communicative need for shape is we see this trade-off that starts to happen where actually their performance on color games starts to just drop. The same thing again happens to complexity. We have this trade-off. Okay. So we have this shape bias that's emerging as we increase the shape, the need to talk about shape distinction. So what exactly is happening there? Well, shape and color here are actually just two dimensions of the same referential space, right? We're talking about these 320 objects. And so if while talking about these objects, we're increasing this need to communicate about their shape, we're actually consequently also decreasing their need to make color distinctions. Color no longer matters as much in terms of making those distinctions. So if you wanted to develop an optimally efficient system that maps to how you use your language, so how you actually use language to communicate, then you would just consequently want to simplify it, not really need to make color distinctions anymore. And so as you increase that need, you end up getting a shape bias that emerges. All right. So I've now shown you that a need to distinguish shape is what leads to a shape bias, at least in our models, okay? How do I then go to people? Well, we know that shape bias is around in people. What about this need to distinguish shape? Is that around in people? Do we have evidence that there is this need? I'm going to say that yes. So I think shape is an affordance of artifacts, meaning that shape tells you something about the function of objects that are man-made, right? So I show you this hammer. You all know it's a hammer, not because of its color, not because of its texture, but it's really because of its shape, right? The shape tells you what it's used for, and the rest doesn't matter so much. And this is true for many man-made objects. And since we talk a lot about these types of objects and talk a lot about function, there may generally be a need to make these distinctions, at least with artifacts. So this gives us testable predictions now. So what are those testable predictions? Well, on the one hand, we should expect the bias to be strongest when things are assumed to be artifacts, right? And on the other, the bias should also be strongest in societies that have access to more artifacts. So if you live in a society where there's just fewer artifacts, we may not expect the bias to be as strong. Well, it turns out we have evidence for both these predictions. So the bias is really strongest when you assume in these experimental setups that you are looking at artifacts of some kind. And as soon as you think that they are natural kinds, like fruits or gems or some kind of natural object in the world, the bias can sometimes even just like fully disappear or at least be attenuated. If I tell you this is a loman, a fruit from an alien planet, and I show you two more, I say, now there's another loman, some of you will have actually assumed that this was the loman, right? And so it really does seem to depend on the sort of assumption that we're looking at objects of some kind that may be man-made or alien-made, right? There's also really recent evidence that actually the bias is strongest in societies that have access to more artifacts. So there's some experimental work that's compared American English speakers versus Tsimane speakers from the Amazon, which is an Amazonian language spoken in rural parts of Bolivia, where they have lesser access to artifacts, and the bias is much stronger in American language speakers and even disappears in some Tsimane speakers. So with this hypothesis generation approach, we were able to generate testable predictions that we could go look for evidence for in people. And once we found that evidence, we can then make the hypothesis that this might also be the reason we have a shape bias in the first place in people, right? Maybe it's just because we have a high need to communicate these shape distinctions, at least when we're talking about artifacts. All right. So what have we learned? Shape bias follows from efficient communication strategies. And there's more to learning than just innate knowledge and learning strategies, but there are biases that emerge just out of the social nature of communication. And it's important, at least, maybe in AI, that we think about the social nature of communication and how that may affect the types of languages and information that we're learning. Okay, so in this particular project, we at least started with a model that didn't really make any commitments to cognitive realism, right? But more was about sort of reproducing these causal pattern that we were seeing. And once we were able to find evidence for the same hypothesis possibly being cognitively real in people, you can sort of move that work a little higher up and say that actually there may be parts of this that do make commitments to cognitive realism. Okay, so to recap today, I tried to answer the question whether or not we could use modern neural networks to study language learning without necessarily being fully committed to cognitive realism. So the yes, I think this is possible. And I talked about sort of two ways of thinking about models, either as tools or as minds, and talked about three approaches that I call weakly cognitive modeling, proof of concept modeling, not the first to call it that, and finally hypothesis generation. I gave 3 concrete examples from my own work, but I want to stress that I'm definitely not the only person doing this. If you're interested in finding some more really interesting work on using neural networks in different ways to study language acquisition, at least these sort of more contemporary approaches, I encourage you to check out our piece where we lay out this framework for thinking about modeling, and then also review all the really cool up and coming work that's been coming out in the last couple of years. So check it out. And finally, some final thoughts about all of this. So recently, what we've been seeing is that most of the work that's coming out is using a sort of proof of concept approach, where we're really making very few commitments, if not any, to cognitive realism anymore, at least since like the mid-2010s. And so I think it's important to sort of stress that, we all know that science moves fastest if we have claims to prove and disprove amongst our community. And so even though many of you have probably come to this talk thinking LLMs have nothing to do with language learning, and I agree with you in some aspects, it's also important that as we think about the role of modeling in the field, and that we believe that it still has a role to play, to be willing to take a little more risks in terms of the claims we want to make. And maybe it is worth sometimes making strong claims, even to be possibly disproved or proven right in the future. And so I'd want to encourage those that are sort of thinking about using modeling to answer questions both about language learning and also just cognitive science in general, to be willing to kind of make these slightly stronger claims. I'm also guilty of this. I tend to try to appease reviewers as well and not make these strong claims, but I think as a field, it's really important that we start to consider them. And so, be it developing models that really are committing to instrumentality, or be it developing models that are cognitively real, I think in reality, most models find themselves somewhere in the middle, right? Where we're kind of thinking about both of these things at the same time. And if we do that and we are clear about our assumptions and commitments that we're making, then using neural networks in the field of language acquisition is very much part of a healthy ecosystem. So on that, I'll thank my collaborators. So Masood, with whom a lot of these ideas were discussed and developed, and then also these are the collaborators on the papers I mentioned as well. So Mike Frank, Dan Drafsky, Gary Lupian, who's also at this conference, Arya Dwan, and finally Alexander Sodram. So
very stimulating. It's going to start now with a comment by your designated discussant, Virginia Valiant.
Hi, Virginia.
Who is Hunter College and will be speaking soon today. Go ahead, Virginia.
Hi, that was such a terrific talk. Thank you. I have a couple of comments and I look forward to your responses to them. I'll start from the end with the shape. So your model takes several epochs or it adopts the shape bias, and it never has the overwhelming. Seems to have about 50% of the time, right? A little less than 50% of the time.
Oh no! Oh, so it's this. So this is particular in we never look at it in the context of like the experimental setup. So really, what we're measuring is whether or not it has the bias in its linguistic system. But we don't actually have the models do sort of the experimental setup we do with people, right? Where we sort of present it with a novel word and then two objects that either share color or either share texture or shape properties. So instead, what we're doing is really measuring the existence of a shape bias in the language itself. So we're really looking at whether or not that shape bias emerges in the language and perception itself, with the initial research question of we know that bias exists in the systems that the parents are using, and that's why we get these sort of experimental results with kids. So we're looking at why does it exist in the first place in parents. Does that make sense?
I think so. So for the model, The facts from
I'm losing you a little bit, Virginia.
Yeah, I'm sorry.
Yeah.
I'm seeing that my connection is on. Let's see if we can go on. So the slide I'm talking about is the one that shows what happens with epics. And there's an initial decline, and then it increases, and then it's stable across successive epics. And it's all
With and or. This is with the and or research where we were looking at like, yeah, that was where I was plotting learning of and or over time. Yeah, over epochs. Yeah. Yes, that block. Yeah.
Virginia, could you turn off your image? It'll make your signal strength better.
Yeah, I'll try that. It doesn't always work, but I'll try it and see whether that works. Can you re-show the shape bias model and the development of the shape bias? I think that'll help make clear what I'm asking about. So what I really appreciate about the way you use this is the interplay between the model's activity and human activity. And that seems to me exactly the way that we would like things to proceed. The model learns to the model has more of a shape bias as shape becomes more important for communicative need.
Yeah, exactly.
Okay, and in the American context, there is a shape bias, and it's greater than in cultures that don't have as many artifacts as the US does. Okay, so do we think children learn a shape bias over time, or do they start right out with a shape bias?
No, so I think most agree that they learn the bias. It's the debate has generally been about how they learn it. So there's sort of two strategies that have been talked about. So one's called associative learning, and the other one I'm blanking on, but the difference is mostly lies in terms of whether or not the bias emerges first in sort of perceptual categorization, sort of independent of language, or if it arises really because we're conditioning on like the lexical categories that parents have. But in both cases, researchers don't necessarily think it's there from the start. It's really one that becomes salient really as the kids learn. So in experimental setups, at least, it doesn't seem to show up really until like the age of 2.
Yeah, that's pretty early, I would say.
It is early, yeah.
So I'm just thinking about the time course of the effects and the extent to which one could actually model the actual environment to see to what extent the communicative need is there, and to see to what extent it does differ depending on the kind of object that's being talked about.
Yeah, it's early, but I would say like, the shape bias is really about noun learning, and by 2, most kids have a decent amount of nouns already in their vocabulary, at least that they understand.
Right.
And many of them will already be saying quite a few as well. But I do think, yeah, it would be interesting from an experimental setup to talk about, in terms of just quantifying how many artifacts versus natural kinds in terms of the nouns that they're being exposed to, are they hearing, and whether or not that seems to map to the amount of bias we then see. I think this would be possible given these really cool data sets that are starting to appear of like headcam data that we have from kids, where we are having children wear head cams for a couple hours a week and looking at what they actually see and what versus what they hear. And so, like Brendan Lake's group has a bunch of research on this data now. And it would be interesting to look at that data and figure out whether or not, are they seeing a lot of objects that we could consider as being, categorized based on their shape, or are they seeing sort of objects that are categorized more based on, their texture, like foods and stuff, right? Because they obviously see a lot of food. Broccoli is broccoli because of its texture and color, not necessarily as much because of its shape, right?
Right. So with adults, one should see a difference in the kind of bias depending on the kind of object that's being described. I don't think anybody's done that yet, right?
Yeah, so there is like a lot of work from like Markman and others that initially sort of argued that the bias was not real, and their argument was built on these experiments where instead they sort of presented them with natural kinds, right? And so as we saw, we know that this bias isn't really present when you present people with natural kinds, and seems to disappear. So it really does seem to kind of be modulated by the type of object you're being presented with. That's the argument I want to make, right? Is that it's only present if you need to talk about it, and that need really arises at least with people because of the type of object, be it man-made or be it a natural kind.
Right. That's great. I see other people have their hands up, but I have one other thing I wanted to ask you about. You mentioned that your agents have an innate bias to color because of how they're built.
Yes.
And so I wondered to what extent you've thought about the relation between what's built in to the models and what the models can do. In one of your papers, you refer to work by Baroni, and he explicitly discusses this question of what's built into the models. So I wonder if you could say more about that.
Yeah, so when we think about, learning hypotheses and using totally general learning mechanisms with our models, the truth is it's impossible to have a model that doesn't have any bias, right? Some way or another, your model architecture is going to introduce biases. I think it's generally true that we don't fully understand most of these biases, and a lot of this research that's been sort of trying to understand the emergent behaviors of these models is to try to figure out like what are their inherent biases. So the bias I mentioned is about CNN, so convolutional neural networks, which are a type of neural network architecture that's used for image processing. There has been a bunch of research kind of looking into these models, and it's also really a structural bias that kind of forces them to consider the localized features, right? Because their input is really, it's not broadly the image, it's the pixels of the image that they're getting. And they then learn to encode relationships amongst those pixels, but necessarily it's a lot easier to encode local relationships between pixels that are right next to each other. And those relationships will often encode things like color, right? Because that's just what pixels encode. So that feature tends to be just much more salient to these models than something like shape requires that you learn relationships between pixels that are all very far from one another. And so that is like a bias that exists structurally in the model. I think in terms of language models, biases are a little less clear. I mean, obviously, a language model like an LSTM, one where we do have a locality bias, because as we move further and further away from, the current state or word we're considering, we are to a certain extent losing information through all of those sort of historical state jumps. But something like a transformer was meant to kind of fix that bias, right? Where we suddenly remove the need to go through previous states linearly, but kind of consider states independently from one another and how they related to one another. And so we were able to kind of remove that bias. Now, most of the language models we use are transformer based, and transformers also have biases that may be undesirable, but by the specific fact that we don't consider the states necessarily linearly, right? Unless we tell them that these words are common in a specific order. And so we know that humans process language in terms of, sequential input. And so maybe there is actually information that's important about sequential input and the information loss that happens over time that we do want to include in our models. And so, yeah, I think it's important to both, as we use models to study people, keep in mind that these models also have biases that we should consider. And in the other direction, as we sort of design our models and think about the information they're going to be learning and how they might encode meaning in language, that these models do have biases that may inadvertently affect what they learn. Yeah, so bias is always going to be present. It's important we understand what those biases are and that we are clear in the commitments that we make, whether or not those biases are going to affect our results in some way or not.
That's great. I have two final comments. One is that a bias is different from content. And we don't know exactly when one or the other is active in acquisition. So that's where the and/or data could be more relevant in terms of it being not just a bias, but maybe something having to do with content. But I think it's much too early to say one way or the other. And my other comment is I was very pleased to see you talk about Gibson's concept of affordances, because it has occurred to me that partly what large models are doing is instantiating that idea that the environment has affordances, and it has different affordances depending on the context. And that seems to me a very nice and important extension that you've made by showing how, with the shape bias, by showing how the context alters what counts as an affordance. So
right.
Thanks very much.
Yeah, thank you so much, Virginia, for the comments and the questions.
Thank you, Virginia. Now, Friedemann had his hand up before, and now it's Charles Yang. Friedemann, has your question been answered, or do you still want to ask your question? Okay, I'll assume that I don't know what happened. Go ahead, Charles.
Thanks for the talk. I really enjoyed it. I have two comments, questions maybe. One is on the first work, the weekly cognitive model part on the vocabulary, acquisition. I'm wondering if before we give too much credit to language models, have you tried a somewhat more sophisticated baseline, like a hidden Markov model, because you can compute surprisal under any language model.
Yes.
And so I'm wondering if you've done some baselining to demonstrate the superiority of LSTM. And maybe just while I'm at it, just the second question is somewhat related to Virginia's point. On the last study, color and shape, I'm wondering, do you make any predictions about acquisition of color and shape words in children? You're talking about how such biases may have been formed, I imagine historically, but I'm wondering if these cognitive pressures are part of human psychology. Do you make any predictions about how fast or how slow, what's the proportion of acquisition of those words in actual children these days? Thanks.
Interesting. Yeah, okay. So for the first question, we did do some baselines with n-gram models. So we tried, so obviously the unigram is frequency, but we also tried bigram, trigram, 4 grams, which also show the same pattern, but it's not as strong. And it seems to be like slightly different per language. So like some languages, bigrams are better. Some other languages, trigrams may be a bit better. Whereas in LSTM, sort of can do a kind of mix of all of those and learn different length dependencies depending on the word. And so we found that the performance with an LSTM was better, but that this sort of generalized to simpler, models that sort of predicted co-occurrence statistics. We had sort of a simplified version of the task as part of the Baby LM challenge that was an optional evaluation that people could run, and we did run it with like the baselines that challenge had, so that were transformer based models. So like a BERT version and a T5 version and so on. But there we only ran it with American English and not on all of Childis. This is based on all of available data on Childis that was uttered to children but not by kids. And those models also seem to show this pattern where the surprisal was a better predictor for age of acquisition in function words and predicates. So it really seemed to be kind of across the board. If you consider context, it matters. I presented LSTMs here because they're sort of the cleanest results where you really see this distinction across all languages, and it really shows this clear pattern. The effects aren't as important when you consider it for individual n-gram sizes independently. You kind of need all, really. If you were to use n-grams, you would kind of need to consider bigrams, trigrams, and 4-grams sort of all in your model, probably, if you wanted to account for all of the words.
Right, that's why we're asking about something somewhat more sophisticated than n-gram, like a hidden Markov model out of the classic framework of statistical models, right? But anyway, I'm glad you did that. I'll be looking forward to seeing those studies in more detail. But the second question is developmental predictions about color and shape word acquisition.
I don't know if we can make that many predictions beyond that. We might expect words to be learned earlier if there's just more need to make those distinctions than color distinctions. But given, I don't know, I have a toddler son, and I tend to tell him colors a lot to distinguish between things. So I'm going to assume that in terms of like, maybe that's why, they develop certain color words before they develop words like rectangle and sphere and so on. Those words don't become that important until much later. And so, yeah, I guess the prediction we would make there is that it has to do with the need, again, to make those distinctions in order to be successful at communication. And color distinctions are important early on if parents use them a lot. Gary
But
has
color words are famously late to acquire by children. And they may say something is red, but they would call a blue thing red. But the shape biases have generally been used to invoke to study the process of word learning. They use shape to guide attention. I'm wondering if you actually say a little more about I guess you can go to the word bank and pull out words to see whether children understand them. So this is a prediction that you can be certainly whatever prediction you make can be easily checked.
Yeah.
Thanks.
Yeah. I'll Gary was on one of these papers too, so I'll let Gary go next. You have a question or comment, Gary?
Yeah. Thanks, Eva. So with regard, a few different points. With regard to color being late, this used to be true, and it seems, at least in some places like the US, no longer to be true. We have this new obsession, new as of a few decades, with teaching toddlers color words, and there's a whole genre, you've probably seen a genre of YouTube videos dedicated to color distinctions. And it takes, my 2 kids went through mild obsessions watching these videos, and after a week of being bombarded, not just with color words, but with the discriminative minimal context, right? So, this is blue, this is red, and everything is blue, right? A blue car is going down a blue slide, right? So it marks it in this very, very high kind of with high informativeness.
Yeah.
But other than these weird cultural quirks, right? Color is not especially communicatively useful, which is why many languages don't have color distinctions. You just refer to the thing by what it is. You don't say yellow banana, you say ripe banana.
Yeah.
But this kind of gets me to shape, right? One other reason why shape is useful is that it correlates with function. So we design artifacts, right, to have certain functions, and function often goes with having a particular shape.
Yeah.
Right. So a spoon it was designed with a particular function in mind, but that requires it having a certain shape. And of course, sometimes shape and function dissociate, right? And that presents learning challenges.
Yeah.
I wanted to also mention that in addition to communicative need, and this is something I'd love to hear your take on. There's lots of complexity in language that seems to have little to do with communicative need, right? So, when it comes to closed class words, it's not that the distinction between definite and indefiniteness, right, is that communicatively critical to warrant words like the and being as frequent as they are. It's not that number is that communicatively critical to warrant having constant, noun verb agreement and agreement between, right, pronoun number and so these agreement systems. But if we also remember that languages are systems that have to be learned by kids, right, and so the elements that make languages learnable in the first place as coherent systems, right, there is a kind of selection pressure to have those elements and to maybe have more seeming complexity than one would predict based on communicative needs alone. And
Right. Yeah, no, for sure. It can't be the only reason that we have languages designed the way they are, but it's definitely, I think, a very important one. There may be, just other things that are just necessary as well in some way, right? For our languages to be productive in some way and allow us to communicate the necessary things that we need to talk about as in human language, like being able to talk about past, present, and future in different ways, or being able to talk about relations in some way, right? And so those are, I think, very different from it can't necessarily be totally accounted for using this idea of efficient communication in how we design our languages. Those will always be present, but they may be present in different forms depending on the language, right? We have some languages have very few sort of function words, but instead have these sort of like clitics or different ways that they change words to account for these types of relations. And maybe communicative need has a pressure there. I don't know. That's beyond my research. Yeah. Maybe I'll take a question from the room because I saw some hands before I. Thank you, Gary.
Yes, just
Yeah.
Wait a second, because I just want to let Friedman.
Oh, yeah.
Friedman, there's a question in the room, and we'll let that be answered, and then we'll come right back to you. Don't worry. Go ahead.
I have a question about adaptation.
I ask the speaker.
I have a question about adaptation. So you said that
Just a second, can this be heard?
I can repeat it.
Okay, good.
you mentioned that the importance of shape in the environment, so the presence of artifacts, is relevant for the application of shape recognition. Do you conceive this more as a personal, as an individual adaptation, or as a linguistic adaptation? Because in the first case, you have a theory of how we learn language. In the second, you have more of a theory of language formation. How I see it.
Yeah.
Yeah.
Okay, so the question was about adaptation, whether or not I see the shape bias as a form of individual adaptation on the part of a learner, or as a form of linguistic adaptation as a whole, as like a system coming up with this as a solution to this problem. I think the way that, we set this up was really to talk about it as sort of a system as a whole coming up with this setup, right? Because we were seeing we argued at least the shape bias emerges because of these pressures from social communication, right? So the need to be able to communicate with others. And given that, I see it really more as like, this isn't something that's about the individual adapting to their learning environment, but us together figuring out a system that allows us to efficiently communicate. And I would say that generally, like, the arguments around like efficient communication are sort of that style, where it's really about like language design rather than individual adaptation to a particular problem. Yeah.
So it is more about the formation of a language.
Yeah, you know, when I yeah, so he repeated, it's more about the formation of a language, and I agree with that. I think when we talk about individual adaptation, at least for me, the way I interpret that is our ability to individually adapt to specific communication contexts, right? So our ability to, if we're talking to one person versus another who may have different cultural backgrounds, or you know, have learned language in different ways, it's more on the sort of smaller scale of how we might interpret how they say things. For example, if you're speaking to someone who's a second language learner of, say, English or French, where we have sometimes these words that actually have different meanings in the two languages, you adapt to that particular person by, you know, understanding what they meant to say, even though they may have said it in a different way. So some, you know, a lot of examples of these words that mean different things, but are said almost the same, right? So
Wait a minute, it's up for you then. Wait a
Yeah.
minute, go ahead.
Thank you very much. Thanks very much, Professor Portelance, for your excellent talk. I think this was very inspiring, very interesting new approaches, and I learned a lot. And now let me ask something regarding the figure you are still showing.
Yeah.
This is obviously the result from this robot interaction,
yes.
right? And did you do or consider doing similar experiments in young children?
Yeah, so this is where models are interesting, right? Because it's a lot harder for us to modulate the amount of artifacts we expose a child to, right? Or the closest we can get to this is really these studies that have kind of compared different societies and speakers of these different societies, where you might sort of think about the American speakers as finding themselves, you know, closer to this 40%, or like the other end of the spectrum, where we talk a lot about artifacts and shape really matters in our language, versus Tsimane speakers being in a society where the proportion of artifacts that kids are exposed to is lessened, and therefore they don't have as much of that shape bias. The reason models are interesting is because we can really do these types of experiments where we do modulate these variables and actually look at the effects and find those causal relationships, which are not as easily done with people. And that's I think where the value is in this approach of using models for hypothesis generation, is that it gives us that ability to do that. Yeah.
But still, may I object? Did you have a condition where you just varied the where you gave color the important functional information?
Yeah, so we don't have a condition where we just give color, because you would end up so we already start when we don't give color at almost 100%. If you give color, basically what happens is they do 100% on color games. So they learn a perfect color naming system because the models already have that inductive bias. But we can do this, you know, with, say, texture. We could do the same thing with texture and we would get the same sort of effect.
Yes, but what's the and what's the communicative relevance then of the color?
So here it's just that the models themselves have a bias towards color. I don't think that humans necessarily have a color bias. And so we don't have that sort of communicative need towards color distinction. If we were, though, then yeah, we would expect sort of the same exchange. So I'm using the shape bias as an example here, but in theory, it could be any sort of perceptual bias could be led by a communicative need to distinguish that particular perceptual feature. And it's just
Sorry,
that it
but
turns out that shape is the one that is salient to people.
sorry, but I'm sorry, I'm really sorry, but I have to disagree in this case, because color is of utmost importance, not only for communication, but also for survival. Think of fruits.
Yes,
Color tells you whether whether this is food, this is in fact food, or
Yeah.
whether it's rotten. It's perhaps even poisonous. So if you have if you look at a banana, in a yellow banana, that's great. If you look at a black banana, this is probably borderline, but if it's white, then something is really wrong, and you might not want to digest it. And inspired by this, it might be a good idea. Yeah, I remember your very instructive example indeed, which you now show again. But I think what this situation should direct us to do is orthogonalized experiments in the same individuals, not across cultures, but across, but the same infants could be put in situations, into language games, where there is an affordance to distinguish color, for example, by having bananas in different colors, as just indicated, and then other strawberries in red and green, and perhaps also in white. Then then there one could there would be a and one could in the language game have a need to distinguish between what you can eat and what you cannot, and you can even go further and have different words in an artificial language, where you have where you have one word for the red strawberry, one different one for the green one, and a third one for the rotten one, and therefore create the need, equal needs, so to speak,
I
to
think that's a really
distinguish
good idea.
across color and across fruit types. And in this situation, it would be really instructive to see what is learned faster by the children, by the real children, not the automata, and to see whether there is still a remaining bias.
I totally agree. I think that's a really great experiment. I think it's one that would actually allow us to sort of extend our hypothesis to not just about artifacts causing shape bias, but instead about
Indeed.
affordance causing perceptual lexical bias.
Right.
I think that's totally true. Given the position we took in this paper, which was really just about the shape bias and affordances, that's not a prediction we make, but you're sort of bringing this hypothesis even to a more general one, which is to say that what guides these lexical classifications is just affordances more generally. And I think that'd be super cool if someone has a lab that wants to do that.
And you could even have two different language games, one in which the color distinction is more important, and in distinguishing between edible and not edible, and then the shape distinction is more important, for example, distinguishing between sweet and sour or something.
Yeah.
Friedemann, I have to interrupt because we're almost out of time.
Thank you so much.
Serge has a question, and Friedemann, stay here because this topic will come up again in the other session.
Sure.
Well, thank you, Eva, for this excellent talk. I would like to hear a little more about how you showed that children learn the inclusive or before the exclusive or. I'm asking that because in my own research, I have shown that adult reasoners usually prefer the exclusive or instead of the inclusive or. And this is because there is more information in the exclusive or, because the truth value is true in 2 of the rows instead of 3. And the rare contexts in which the inclusive or is taken into consideration by adult prisoners is when they don't have any choice because the context imposes it. For example, and in our experiments, you say you can have this, you can postulate for this job if you have a doctorate in cognitive science or in computer science or 10 years of experience in programming. And in such a context, it's obvious that the one who has the doctorate and the 10 years experience has more chances to get the job. But in most contexts where in most open contexts, you don't have this, and people prefer what is logically less probable and more informative, the exclusive instead of the inclusive. So can you say a few words about your experiments?
Yes, so I don't personally have experiments with people or with kids, but others have. I think they sort of match what you're finding in the sense of, in terms of like the exposure that kids have. So there's this research that basically looked at in childless data and what the interpretations were and whether or not you could have an inclusive or not. And most of what kids are being exposed to, just like in naturalistic context to adults, tends to be this context where really there's just an exclusive interpretation that is better. Not to say that inclusive is necessarily unavailable, but it may be made unavailable through how people use prosody in those contexts. And I say, do you want orange juice or milk? Something like that, right? That necessarily marks it as an exclusive, but also there are contexts where it just necessarily you can't do both. And then there are contexts where it's somewhat ambiguous, but the kids are still sort of interpreting it in some way. I think the research that has looked at like their interpretations of or in these contexts where you could have both, there are experimental studies that are done with kids usually around like the age of 5. Or and are learned pretty late. Well, or is learned pretty late and is learned a lot earlier. Where they have these contexts where they want to see whether or not kids are choosing in the sort of ambiguous setting to interpret it as they can only pick one or they're allowed to take both. And they do find that generally like kids don't seem to initially have that exclusive interpretation.
Thank you. We have worked just with adults, so.
Yeah, which is why they think that maybe they learn it first. But yeah, in terms of the input that kids are getting, it is just like adults, it tends to be mostly exclusive.
Yeah.
And so that's where that debate sort of started, is this doesn't silly sort of match up to these sort of learning hypotheses, these are what are called in the field like usage-based hypotheses, where it has to do with the type of language that kids are being exposed to.
And contexts are very important.
Yeah. So yeah.
Thank you.
Yeah.
Thank you.
Okay, thank you very much, and everybody say. You need a little rest because we're starting in a few minutes again.